This is Blocks 2, the hardest cryptographic challenge of the event, and likely the hardest challenge overall. It involves implementing a well-known cryptographic technique called a padding oracle attack. The actual interface the user is presented with is relatively simple. There are two operations they can perform: encrypt and decrypt a message. To encrypt a message, the user enters the message they wish to encrypt. This is added to a data structure which contains both the message as well as the flag. This structure is then encoded using JSON and encrypted using AES CBC mode. The IV and ciphertext are both returned to the user. The decryption routine is similar. The user enters their ciphertext, which is split into the IV and strict ciphertext, and then the ciphertext is decrypted. At this point, the algorithm attempts to unpad the decrypted message. However, if the padding fails, it returns an error message. Otherwise, the JSON is loaded and the value is returned back to the user. There are two specific ideas that we must understand in order to understand the attack that will be implemented later on. The first is message padding. Block ciphers encrypt data in blocks of an exact size. For AES, this is 16 bytes. However, this example will use 8 bytes. If we have a message, such as long piece of text to process, in order to encrypt this, we must first break it into blocks. You can see here that I've broken it into successive 8-character blocks, except for the last block, which is only 5 characters. This last block cannot be encrypted by AES because it is not the correct size. In order to make it the correct size, we must use a padding scheme. The padding scheme that is used is very simple. You look at the number of bytes that you need to append to make the block the correct size, and you set each of their values to that number. For example, we need 3 bytes here, so each of the bytes is of value 3. If we had a different piece of text, this is a different length of the final block, which means we only need to have 1 1. Similarly, you can imagine we might have 5 5s or 8 8s depending on the length of the message. Note that we are using the actual value 1 and not the character 1, which has a value in hexadecimal of 31. The second concept that you need to understand is how CBC mode works. In order to encrypt a message using CBC mode, you start with your plaintext broken apart into blocks. You also must pick an initialization vector, or IV. To encrypt the message, you take the plaintext and XOR it with the initialization vector. You then encrypt this result to produce the first block of ciphertext. Along with this, you XOR the second block of plaintext with the output of the block cipher for the first block. This results in the second block, which is then chained into the third block, and so on. This is why the system is more secure than ECB mode, as demonstrated in the previous Blocks 1 challenge. To decrypt, the process is very similar. First, you take a block and you decrypt it. Afterwards, you XOR the initialization vector to produce the plaintext. This has a subtle but powerful flaw. If you imagine making a modification to a single byte of the second to last block of ciphertext, the first thing it will do is go into the block cipher and completely ruin that block. However, it will also result in a change to just the last byte of the last block of the ciphertext. You'll notice that this is the same area where the padding was applied to the message. We can leverage this behavior in order to completely decrypt any message using CBC mode. Imagine first off that we have a secret value that has been padded and then encrypted, and we're able to decrypt it without seeing it and check whether the padding is valid or not. Normally, the padding would be 5 5s. However, if we start changing the last byte of the second to last block, this will create a change in the last byte of the last block. In most cases, this will result in invalid padding. However, if we guess correctly and happen to set the last byte to the value 1, 1 becomes valid padding. The message is interpreted as secret value 5555, which is an incorrect value. However, we know the exact value of this last byte since we forced it to 1. Using this knowledge, we can then modify the ciphertext so that we force the last value to 2, and then start making guesses for the previous character. Only when we successfully guess the change which forces it to 2 will we obtain another valid padding, 2, 2. Similarly, we can repeat this process for 3, 4, 5, and so on. Now let's look at the actual solution script. The first thing that we do is establish a connection, and then we obtain the actual ciphertext value that we wish to decrypt. In this case, we're using the test input value as our message, since it has a roughly nice length. After obtaining the value, we proceed to the main part of the attack. We first compute some relevant numerical values, and then proceed to constructing the different parts of the message. You can see that the actual message that's being submitted is made of the first part, which is unmodified, a single byte for the guess that we're making, a part called modified part, and then an unchanged part called last part. Last part corresponds to this final block, which we do not want to touch since we're making modifications to the block immediately prior to it. Modified part are the values that we already know and are modifying to the new target value. For example, in the second step, modified part would be the change to A, which forces the last byte to 2. The guess is, of course, the guess. We simply iterate over every possible value of the guess byte until we find a result which does not return a padding error. At this point, we have correctly identified exactly what the change must be, and we compute the raw value of the plaintext through this simple calculation of 3 XORs. It's important to note that we also must strip off any additional blocks from both the modified section and the last section of the message. Imagine if we were to try and change more than 8 consecutive characters. Our changes would spill over from the earlier block into the later block, which means that we'd attempt to propagate a change from the previous block into the later block that's already been garbled because of the modifications to it. Due to this behavior, we need to make sure that the modified part and last part are both no more than 1 block long. Running this script will produce a rather satisfying result. You can see that each character is being obtained one at a time over successive guesses. And slowly but surely, we see the flag being printed out. You'll note that it is making 1 to 200 guesses per character, and so this is completely infeasible to perform by hand. Here we can see the flag, SC6, last but not least.